Hi, I'm Min Li from Penn State. I'm going to present our work DSOAP from my advisor Professor Sampson and myself. DSOAP stands for Dynamic Spatial Orientation Affinity Prediction. And I'm going to show you how our DSOAP schemes predict orientation dynamically for caching in multi-orientation memory systems. You may be wondering what we mean by orientation or multi-orientation memory, and why do we need dynamic prediction for this? So let me explain these first. There are many multidimensional data structures. For example, this table, where we have records in row dimension with students and fields in column dimension with various information. Of course, there are scenarios where we want to retrieve data from both dimensions, like this example where we want to know all about the student with minimum height. However, we long had the problem that when storing data in conventional memory, we need to orient data onto 1D memory layout. Only the dimension that's oriented to have row orientation, which means with unit stride address in memory, is dense. Other dimensions are sparse, and accessing along those dimensions only get one useful element per axis in row orientation. Similarly, conventional caches can only store data in one orientation, and data along other dimensions takes multiple cache lines to store. This results in a waste of the memory bandwidth and cache space for every level in the cache hierarchy, leading to performance overheads. We have been living with this problem forever, but we don't have to anymore. Recent works have developed memory systems with what we call MOM, multi-orientation memory. These systems provide dense data in multiple orientations, leading to more than 3x speedups over conventional system on some workloads. The multi-orientation main memory in a MOM system can provide data in row orientation, as well as other orientations where the contiguous data do not have unit stride address pattern. Due to address decoding complexity, these other orientations usually have simple address patterns, such as regular non-unit stride. And we call it column orientation when the stride is hardware dependent. Prior works have presented MOM implementations with different technologies. Technologies used for multi-orientation main memory cannot be applied to the entire cache hierarchy, hence the most common cache organization in prior MOM works is physically the same as conventional cache, but has an additional field to indicate the orientation of cache line data. But MOM systems also comes with a new challenge. When there is a scalar access request, it can be fulfilled with data in multiple orientations, and the choice on what to cache has to be made. Ideally, if we knew the future access pattern, the orientation that results in less data transfer would have been preferred. To figure out which orientation is preferred, PROMOM works rely on static analysis, similar to what we already do for data layout optimization. And they extend the ISA to indicate oriented axis. We call this static orientation annotation. However, this only works if two assumptions were true. First, static analysis only works if the preferred orientation is statically analyzable. Second, the static orientation annotation only makes sense if the preferred orientation is always the same for a given instruction. But no, neither of these assumptions is true. This is what we call orientation dynamism. The preferred orientation is not always statically analyzable, nor is it always the same for a given instruction. Orientation dynamism comes from many sources. For example, some code are just not statically analyzable because the access addresses are unknown at compile time. And even when the addresses are known, whether some accesses happen can be data dependent. In this indirection example, arrays X and Y are accessed through an indexing array IC, and when the content of IC is unknowable at compile time, so are the addresses to access in X and Y. Yet, depending on those addresses, if the accesses are dense within X and Y, accessing in row orientation is preferred. And if they are sparse, column orientation is preferred. In this in-memory database query example, the address of each element is known at compile time. However, whether to access fields F1 and F2 depend on the value of F3, which means that with the same query, depending on the data distribution in F3, F1 and F2 may be rarely accessed, in which case retrieving both fields in row orientation would be preferred. Or they may be commonly accessed, in which case retrieving them separately across multiple records in column would be preferred. Both examples show that while static analysis fails, the preferred orientation could have been analyzed if we had runtime information. This means that orientation should be determined dynamically at runtime. There are also other sources of orientation dynamism that we do not address with DSOAP. You can read more about those in our paper. To collect runtime information, we can either use a software or hardware approach. And DSOAP uses a hardware-based approach because this imposes no complication on software, requires no ISA change, and is available to all regardless of software runtime analysis availability. DSOAP is a hardware-based runtime approach that dynamically predicts preferred orientation. When using the best information source, DSOAP tracks preferred orientation across dynamic cases, avoiding slowdowns of up to 2.7x, and provides competitive performance to prior static analysis approach on static cases. For the rest of the talk, I'll go into more details on the implementations of DSOAP, and then show you how DSOAP manages to track the preferred orientation dynamically with only 2% overhead on average. Here is an overview of DSOAP workflow. In the L1 data cache, we introduce a small instruction PC indexed cache called OPT, Orientation Prediction Table, where we store the predicted preferred orientation regardless of how it is predicted. Then, when there is a scalar axis miss in the L1 cache, we look up for the predicted orientation in the OPT to generate oriented miss. Unlike prior static approach that gives all axes an orientation, we apply the predicted orientation only to L1 cache miss, because as long as we can satisfy a scalar memory axis, we don't care what orientation it was in. This means that preferred orientation is a property of cache field data. But how to fill up the OPT to actually have predictions in it? Remember that preferred orientation results in less data transfer. This can be roughly translated into data utilization, since more useful data per transfer means less transfers required. We also note that different orientations have different address patterns, usually regular strides. Hence, if we can identify the runtime axis pattern, we can compare whether it fits into that of an orientation or not. For this, we can use stride analysis or prefetchers. Utilization, stride, and prefetcher are the three information sources we explore for DSOAP. We extract these information by analyzing past axes and devise 5 prediction methods using them separately and combined. We cover all these schemes in detail in our paper, but due to time limit, we'll focus on those using the best information source, utilization, in this presentation. We devise our DSOAP use scheme with utilization-based analysis. On top of the basic DSOAP workflow, we add a structure called IIUB, Inter-Instruction Utilization Buffer. IIUB keeps a history of L1 MSHR misses and observes subsequent accesses to record how much useful data fall in the same cache line as the miss in any orientation. The IIUB entries consist of miss address, miss instruction PC, and bitmaps to record the utilization of cache lines in each orientation. Let's look at an example to see how utilization is recorded and used to predict preferred orientation. To begin with, we have an MSHR miss, and we create an IIUB entry with its miss address and access instruction PC. This address falls in the 4th element in row cache line and the 1st element in column cache line. Hence, the bitmaps are marked with 1 at these places to represent used data. Now, when a new access arrives, we use mechanisms similar to that used in MSHRs to identify if it's in the same cache line as recorded IIUB entry. In this case, it's in the same column, so we mark the corresponding element in the bitmap to be used. Now, this new access also misses in the MSHR, which creates a new entry in the IIUB. We repeat this process for every new access and MSHR miss. If an access falls in the same cache line with multiple entries at the same time, we update the used data for all those bitmaps. Finally, when an entry is evicted from the IIUB, we count the number of used data. Here, we've got 1 used element in the row cache line and 3 in the column cache line. This means that the column orientation has higher utilization, and we update the OPT to record that this instruction prefers column orientation. Next, let's go over quickly on how stride-based analysis works with our DSOAP S scheme, and how we combine utilization and stride information together to make DSOAP US scheme. On top of the basic DSOAP workflow, DSOAP scheme extend the OPT entries to keep the last accessed address and stride information to perform the same analysis as L1 stride prefetcher, and when a stride pattern is found, is compared against the patterns of orientations to find the best fit. The DSOAP US scheme combines the utilization and the stride information by storing the bitmaps from IIUB in the OPT, and then complement them with stride information before counting for prediction. Finally, let's briefly look at how information from lower-level prefetchers work with our DSOAP P scheme, and how we combine this with the other 2 sources into DSOAP USP. We explore lower-level prefetches as an information source, using best offset prefetcher as an example. We use the prefetcher to identify access patterns and compare that against different orientations patterns to generate predictions. Then, this predicted orientation is passed along with the response data to L1 and combined with the PC to update the OPT. The DSOAP USP scheme combines all three information sources together by simply using DSOAP P's prediction when DSOAP US cannot provide stable prediction, but this nearly never happens. The complete methodology is described in our paper, but briefly. We evaluate our DSOAP schemes on a MUM system simulated with Gem5 for CPU and MUM caches, and with NVMe for the multi-orientation main memory. As for our DSOAP schemes, all of them use a 16-set, 4-way associative OPT. We use benchmarks from where MUM systems works and split them into two categories, with DVD, data value dependent benchmarks including 13 queries from RCNVM, and DVI, data value independent benchmarks including linear algebra and HTAP workloads from MDA cache and gather-scatter DRAM. These benchmarks from prior works do not outline the orientation dynamism due to their static annotation nature, and we have included our own dynamic micro-benchmarks with parameterized orientation dynamism to highlight the relative sensitivities of static and dynamic approaches. These include two workloads matching the examples used to explain orientation dynamism. Let's look at the dynamic micro-benchmarks results first. For the indirection workload, we show 4 co-indexed arrays that are aligned in MUM layout. And if we only had static analysis, we would have either used the row option that always accesses everything in row, or the D1 option that always accesses the 4 co-indexed arrays in column. However, we can see that depending on the IC array's density, the preferred orientation for these co-indexed arrays change, and static annotation will result in significant overhead in some cases. In comparison, while DSOAP-S and DSOAP-P schemes fall short to track this change due to their pathologies, the utilization-based DSOAP-U star schemes make the best decision on preferred orientation across all dynamic cases, with less than 1% overhead on average. Similarly, with data-dependent queries, we can devise multiple reasonable static orientation annotations. Here, accesses to fields F3, F4, F7, and F8 depend on the value of F10. We can either use option D2A to access only F10 in column, or option D2B to always access all 5 fields in column orientation. Row is also given as a reference here. The results again show that which option is better is dynamic. This depends on the distribution of data in F10, and the wrong static annotation can result in slowdowns of up to 2.7x. And though DSOAP-S and DSOAP-P schemes still don't work well, DSOAP-U star schemes also still manages to track the best orientation option with about 2% overhead on average. Finally, let's see how DSOAP compares to the static analysis used in prior works on the benchmarks they used. Here, static options refers to the static orientation notation used in prior works. Let's zoom in on the geomean results. We can see that the DSOAP-US scheme shows competitive results with 4% speedup in data value dependent benchmarks, around 2% speedup on data value independent ones, and 3% speedup overall. In conclusion, MUM systems need orientation affinity on memory accesses, and prior works use static analysis for this. In this work, we have shown how orientation is dynamic, and this demands dynamic orientation assignment methods. We have presented DSOAP schemes and explored multiple information sources for dynamic orientation prediction. And we have shown that utilization-based DSOAP schemes shows competitive performance on static orientation workloads and tracks best orientation on dynamic orientation workloads with only 2% overhead, avoiding the significant slowdowns of up to 2.7x of static annotations. That's all for this presentation, and you can find out more about DSOAP in our paper. Thank you for watching.